Hello and welcome to another video. So in this video we will see how we can use a controller to stabilize a plant. So we have seen open loop and closed loop control. So this is the plant. So the transfer function of the plant is Kp divided by T1s plus 1 into T2s minus 1. Now before going into the details, I'll just explain what is the zeros and poles of a transfer function. Suppose this is a transfer function. The roots of the numerator are called the zeros of the system. And the roots of the denominator are called the poles of the system. So here the zeros are, whenever you equate this to 0, you will get the roots as -1 and -2. So the zeros of the system are -1 and -2. Similarly, the poles of the system are, when you equate the denominator to the 0, you will get the roots as s equal to 0, -3 and -4. So these are the poles of the system. The values at -1, s equal to -1 and -2, we get the entire transfer function as 0. That is why it is called zeros of the system. Similarly, when the value of s is 0, -3 and -4, we get the entire transfer function at infinity. The value will be at infinity because the denominator is 0. Now the entire transfer function will be infinity. So once you substitute the value of s to be either 0 or -3 or -4, one of these terms will be 0. So the denominator will be 0 and there will be some value x in the numerator. But this entire value of the transfer function will tend to infinity. So that is why it is called poles. The value tends to be infinity. So it rises to infinity. That is why the name pole. So now we will go back to the closed loop system. Here in this system, we have the controller C of S and we have the plant Kp divided by T1s plus 1 into T2s minus 1. Now the time constants T1 and T2, the time constants of the system T1 can be less than T2, or, so this is the first condition, or T1 can be greater than T2. So these are the two cases, two possible cases. Now, each case, either in case 1 or in case 2, a proportional controller is sufficient to stabilize the system. So in which case does a proportional controller, so a proportional controller is nothing but the transfer function of a proportional controller is just a gain. Here I'm taking as KR, so that is a constant value. So when KR is applied in place of C of S, we will find out the entire closed loop transfer function for this entire block and calculate the stability of the system. Now the closed loop system, closed loop transfer function will be, so I am applying the formula G of S by 1 plus G of S H of S. Since there is a negative feedback, we can use 1 plus G of S H of S. Now after applying that formula, we'll get the transfer function to be something like this. And I'm simplifying that. Instead of C of S, I am substituting it to be KR. After simplification, it is KR KP divided by T1s plus 1 into T2s minus 1 plus KR KP. So this is the closed loop transfer function of the system. From this closed loop transfer function, we will analyze the stability of the system. So for that, we will take the denominator. The denominator is called the characteristics polynomial. It is from this characteristics polynomial that we will find the sufficient conditions that is required to stabilize the system. So I'm taking this denominator alone and I'm analyzing it. So this is the denominator of the transfer function. After simplification, I get T1 T2 S square plus T2 minus T1 S plus KR KP minus 1 equal to 0. So for this entire closed loops, for the entire system, after the controller, after applying the controller, proportional controller, we will get this denominator. So all the terms in the denominator should be positive. That is condition, that is a sufficient condition to stabilize the system. So from this first term, we will get T1 as well as T2 should be greater than 0. Similarly, from the second term, we will get T2 minus T1 should be greater than 0. T2 greater than T1. So this is the condition. This is a sufficient condition for the system to be stabilized by using a proportional controller. We started with initially with the proportional controller. So whenever a proportional controller is used, this condition should be satisfied for the system to be stable. And from the third term, we will get the condition KR should be greater than 1 by KP. So from this three different conditions, we get to know that T1 value should be less than T2. Whenever for a proportional controller is used, T1 should be less than T2 so that the system is stable. We have seen that for the proportional controller, T1 should be less than T2. So now suppose this condition is not satisfied. We are dealing with the condition T1 is greater than T2. Now in that case, we will have to use another controller. So proportional controller cannot work, cannot stabilize the system. So we will use the proportional derivative controller. So we will add the derivative term as well. So KR1 plus TVS. So in that case, we will see what will happen. First, I will derive the closed loop transfer function. So the transfer function here is, this is the controller part, KR into 1 plus TVS. So the closed loop system will be, the numerator will be like this, and the denominator is 1 plus G of S, H of S. Here H of S is 1. So this term is the G of S part. And after simplification, we will get a simplified term like this. And the denominator is called the characteristic equation. We will use this characteristic equation alone to analyze the stability of the system. Now, these are the three conditions. After a simplification of the characteristic polynomial, I get the terms like this for square, S, and the constant. Now, all these three terms should be positive for this to satisfy the sufficient condition to stabilize the system. So now T1, T2 greater than 0. From the second term, I get the condition that TV should be greater than T1 minus T2 divided by KR KP. So the derivative time constant should be greater than T1 minus T2 divided by KR KP. And KR will be greater than 1 by KP. That is the third condition derived from this. So if these three conditions are satisfied, then the system is stabilized. Even if we are dealing with a system where we have T1 is greater than T2, a proportional derivative controller will be able to stabilize the system. So this is how we analyze the stability of a controller, stability of an entire closed loop system when a proportional controller and a proportional derivative controller is replaced. So only will be conditions where a proportional controller alone cannot satisfy the stability of the total closed loop system. So there we will go for either PD controller or PI controller or PID controller. So we will see a few more examples in the next video. Thank you.